And our next speaker is Yaacov Kopeliovich.
Okay, thank you very much for inviting me to talk in this conference. It is a pleasure to be with you. And hopefully next year we will be in person. So what I want to talk about today is about a classical topic, which is a fundamentals identity for theta derivatives with rational characteristics. So we are talking about one-dimensional theta functions evaluated at certain point on the elliptic curve. And for marketing purposes, it's also a solution of Mumford's second problem, okay, about relations, one-dimensional relations of theta functions. So the agenda will be as follows. First, we are going to talk about problem statement. Then we will talk about preliminaries. Then we'll talk about the fundamental theta derivative identity. And then I'll show you how to do the theta derivative with rational characteristics. And then at the end, you'll see a plethora of examples, you know, how we can derive specific relations between those theta functions. Now, this is kind of an object which goes basically to the beginning of 19th century. So when people started to think about elliptic integrals, they discovered these functions as generalization of the trigonometric functions. And from that point on, they were always fascinated by the relations that those functions produce, because the formulas are really aesthetically, they're very pleasing. Okay, so the first identity, I don't know if you guys, is this identity, which basically says that if you have a theta derivative evaluated as a certain point, half-half. So if you think about the fundamental parallelogram, the half of an elliptic curve, the half-half is the middle point, right? So that's the theta derivative evaluated at a middle point, which equals to the product of the theta derivative of the thetas, which is evaluated on the other point of order 2. So if you have a parallelogram, think about these 4 points, 0, 0, 0, half, 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 and half, 0. The half, half is this. And the other 3 points are coming on the other side of the, you know, of this equation. And then you need to multiply it by pi to get the exact formula, okay? So that's called the Jacobi theta derivative identity, because in his big magnum opus on theta functions, Jacobi actually derives this identity. Okay. Now Mumford has a very famous 3-volume Tata lectures on theta of theta functions. The first volume deals with the one-dimensional case. The other 2 volumes are dealing with the multi-dimensional case. In the one-dimensional case, in one of the problems, Mumford says, can Jacobi formula be generalized? So if we, for example, replace this half-half with some other points where we evaluate the theta functions, right? AB, where AB belongs to Q. So that's kind of a rational point, not on the elliptic curve, but inside this fundamental parallelogram. Okay. He asked whether it can be expressed in cubic polynomials in other theta. So it's actually very similar to this formula, right? But he actually loosens it a little bit. He says, okay, I don't think we're going to have such a beautiful product, but maybe we can get a polynomial, okay? So that's what his question. He had a second part of the question, which I don't want to discuss now. Maybe we'll discuss it in the future, okay? So if we put it into our language, right? We take so we basically change the notation somewhat. Now we take the derivative with respect to z. So 0, right, is a z, is an argument of the complex plane. So we want to take the derivative evaluated at certain points, right? Here they are rational, but they don't need to be rational per se. We want to express them through the first order, you know, through the theta functions themselves. Okay? So it's a very straightforward problem. Okay? And what we obtain, right? We do not obtain polynomials. Our result is that we have rational functions in this, but the degree of the rational function is exactly 3. So you have a rational function where the denominator has a degree 3 above the numerator, where the degree is kind of very intuitive concept. Okay. So the homogeneous degree of these 3, so it's actually very close to what Mumford has, but you are going to replace a polynomial with a rational function. Okay. So I don't believe that we can get a polynomial. I think to get a polynomial is a fool's dream, but I may be mistaken. But I think that, so my kind of belief that this is the best result that we can get. So what I want to do, I want to explain, right? How do you get something like that? How do you even think about relations between these functions, okay? So the first thing you want to do, you want to define a set of functions. So the set of functions that you define, it's an argument of two elements. The first element is a complex number. The second element is an element of the upper half space. Okay, tau. Okay, so it's linear, it's quadratic in tau, it's linear in Z. And it satisfies this kind of relations. Of course,
Yaacov, I'm sorry, but we see only the first slide of your talk.
Really?
So maybe you write something or not.
Our screen sharing is paused. Let me just see why it's paused. Can you see it now?
Yes. Now we see.
Thank you very much, Sergey. Thank you very much. Okay, so once again, right, it's basically the fundamental problem is to express zetas through the cubic polynomials. That's the goal that's the goal here. Okay. Okay, so do you see the beautiful picture? Good.
Yes.
Right. So basically, this kind of explains where this function is coming from. So Z is a complex plane, but we want basically to build the functions on the fundamental polygon of the elliptic curve, which is characterized by tau, right? So this is 1 and this is tau, if you want. And tau is belonging to the upper half plane, right? But we cannot, of course, we cannot build the holomorphic functions because of Liouville's theorem. If we have 2 periods in a complex plane, it will be constant, right? So we go to the next best case, that we have something here and we have something here, which is linear in Z, okay? And in here, because I move in tau, I just have e to the minus pi I tau. Usually it's quadratic if I move by n tau, it will be I n squared tau. And you can see it here from here, you know, the formula here is actually pretty straightforward, right? So it's an infinite series, but it converges and, you know, it is actually behaves very, very, very nicely. Okay. Now, what you want to do here, you want to actually move the Z and the tau and the Z, you want to move it by a certain number, right? So if you take the Z and you move it by epsilon prime, you basically get the zeta function itself where you move tau by epsilon prime, you move the first variable Z by epsilon, right? And you just multiply by a certain factor. So when you look on this zeta epsilon prime, when you look on this zeta function with what we call zeta function with characteristics, you can actually think about them, right, in the 19th century way, like basically a translation of the original zeta function multiplied by a certain factor. And if you're moving to the 20th century, right, you think about line bundles that are associated with the divisors of an elliptic curve, right? And then this guy will be just a section into a certain line bundle, which is actually associated with the divisor defined by epsilon prime. I tend to think about them as a 19th century guy, but you know, I know that a lot of people don't like that, so you can think about them as line bundles if you want, no problem. Sections into a line bundle, okay? So here, for example, you have an example. So you have basically, so this identity, right? The theta prime half 0 tau is non-zero. Why? Because it's because theta half is actually an odd function. So theta half evaluated as 0 is 0. However, the derivative of theta half is not 0. And the derivative of theta half, okay, evaluated at 0. So basically, the theta function, which with the derivative of the theta function, which is associated with this point, equals to the product of the thetas, which are associated to the other 3 points, right? So it's actually very natural, very kind of a beautiful combinatorial picture. Okay, and then of course you need to multiply by pi, otherwise it won't work. So you have a constant here. Okay, not a bad deal. Okay, so that's an example of the classical Jacobi identity. Now, what we have here, we have basically transformation properties under the lattice, right? So what we want to do now, we want to develop identities similar to this identity, but for the derivative evaluated at other points, like say rational points. So what we want to understand, we want to first understand the elementary behavior of this function. And the behavior is actually very, you know, the behavior is actually pretty straightforward. You can see that if you take this z and you move it by an element of the lattice. So when I talk about the lattice, I talk about basically the fundamental polygon where I kind of take this guy like 2 times here and then maybe 4 or 5 times here. Okay. You can see that it's actually go back to the same point, but with a certain product. And once again, the crucial thing to observe that this is quadratic in tau, but linear in z. Because here you have mz plus epsilon minus n minus epsilon prime. So this is linear in z. And here you have m squared tau. So this is linear. This is kind of quadratic in tau. And also, when you move the characteristics, you also by an integer number, you also get some, you know, you also get the function back times certain, you know, times a certain factor. And here you also see that. So here the difference between m and n, that these are integers. These are not integers. These are actually any real number. So this you can think about that you are just moving the original theta with you know, by an element of a complex number, okay, which is defined through tau and 1. Okay, so then once again you can see that these functions are invariant, right? So basically, when you move them, you just get the characteristics and you multiply it by a certain, once again by a certain factor, which is once again just like in the first case, is actually quadratic in tau and actually linear in z. Okay, so you have this kind of invariant properties of these functions, and these invariant properties are basically the only basic ingredients that you need to start building relations. And here's another one. That's basically the derivative, right? So how do you get this? All you do is you take this guy and you just derive by z. And then, you know, here you will get theta prime, epsilon prime. So you will get this. On the other hand, you have some formula. Okay, so you use the product rule to derive it. That's it, right? That's all there is to it. Okay. Now, the crucial thing about this is that theta epsilon prime z tau has a unique 0 in the fundamental parallelogram with size 1 tau corresponding to an elliptic curve. So this function, right, has only 1 0. And you know, and furthermore, you know the 0. Okay. Now, the proof is actually very simple. First, you kind of verify. You use the formulas here to verify that this guy is actually 0. That you take, if you take this point, you substitute into z. You can use these formulas, and you basically get that it's 0, because epsilon prime, when you play this game, epsilon prime plus s prime epsilon s will be 1, 1, and z will be 0. So theta 1, 1 is 0 tau. This is easy to see. Okay. And now, how do you know that it is only 1, 0? You just use the counting argument of the residue theorem, and we're done. So that's what we have here. So this is an example that you have basically the characteristics 1 over 6, 1 over 5 is actually going to be 0 in this. So you take half minus 1 over 5 plus half minus over 6, and you get this point. And you can see that it is actually 0. So, you know, basically half is odd. So then when you do the, the accounting here, you get that when you substitute this point here, you will get the half at 0. And then what you do here, right? And then you basically, you want to count the number of zeros. So you can just do the d log of this function inside the fundamental parallelogram. And because of the invariance properties, okay, you just get that you have only one. It's you know, I mean, in complex analysis, I see in complex analysis 1 or 2, the undergrad or grad, they do it. I don't know the program now that other universities have. All right, so now we are looking on this complicated identity, okay? This is what we call the fundamental set identity. Why this is a fundamental set identity? Because of this identity, you can actually get the solution for the Mumford's problem, okay? So it looks actually very, very scary. Oh my God, what's going on here, right? And this identity is true for any characteristic. Now, the question is, how do you prove something like that? Okay. And the proof is actually extremely easy. So you basically look on epsilon prime and delta prime, any characteristics. It's not need to be rational, right? And you just have this kind of, and you have this requirement that 2 epsilon plus delta equals half and 2 epsilon prime plus delta prime equals half. It's a very strange requirement, and I'm going to explain in a moment why we have this requirement. Well, all you need now to do is to consider this function, right? So you take the half to the cube, and you have the theta epsilon prime in square times theta delta prime z tau. Now, the fundamental claim is that this function is periodic on the fundamental parallelogram. And how can you prove it? Well, all you need to do is to go here back to this formula. And you know that theta half z plus tau m plus n equals to something times theta epsilon prime z tau. And then in the denominator, you also have this kind of expression, right? So you basically get the same functions with some factor. And lo and behold, those factors cancel out. Because of this requirement, when you do the calculation, you will see that basically the factor up, the factor down, when you move by a lattice, cancel each other. So this is going to be an elliptic function. This is going to be a function, right, which is periodic under 1 and tau. If you don't want to talk about elliptic curves, don't worry about it. Just look on that as a function which is periodic in 1 and tau. That's it. Now, how can a function be periodic inside 1 and tau? It cannot be analytic. It has to be meromorphic, right? So if we have a meromorphic function, what do we know about the residue of a meromorphic function inside the parallelogram? What is the sum of the residues? What is the sum of the residues? 0, right? It's a residue theorem. That's it. So,
may I ask? This is because on the parallelogram the quotient will be the torus, yes, and this is
exactly right. Exactly. So the quotient is a torus, and this is a function on the torus. So you take the residues. The sum of the residues equals 0. You're done. It's complex analysis 101.
No, but this is because of Euler characteristic of torus. This is
yes,
another.
Exactly right. Yes. Yeah, but you don't need, I mean, you don't need to think about, right? You are thinking about like, yeah, you can think about this in a simpler, I think about this in a much simpler term, right? That if you have something, right? If you have, let's say, a closed area inside the complex plane, right? And you look at function, the residues of this function equals the sum of the residues of this function inside this plane equals 0. So yeah, you're right. It's because of the, yeah. But I'm a simple-minded man, you know, so I think about this as complex analysis 101, right? So you have this kind of quotient, and you can just calculate the poles. Once you calculate the poles, you calculate the residue, you're done. You just sum the residue, you get the relation. So the pole, there are two, okay, so if you look on the denominator, I think you can know exactly what the poles are. You have here a square, right? So it has to be a 0 of order 2 of this function, that's this one. And you know that this is a simple pole, so you know that this is a 0, okay? And now what you want to do, you want to calculate the residue, okay? That's it. The residue here, sum the residues, and you're done. That's it. You don't need to do anything else, right? So the residue of f equals 0 inside the fundamental parallelogram. And when you do the residue, now, okay, now you need to do accounting, right? You need to calculate the residue. So it's a quotient of the form f divided by g squared. This is a g squared, right? So you need to know the formula for the residue of f divided by g squared. Okay, so we kind of, you know, you can calculate it yourself. We do it for you on the slide, and we get this kind of relation. That's it. We're done. Okay. So this is what we call the fundamental relation. Now, how do we get from this fundamental relation, which we obtained by the residue theorem? How do we get it to the? How do we get to this solution that we claim that we solve the Mumford's problem? Okay. Yeah. So basically, here we okay. So what we want to do here, right? We want to actually calculate it. And now we basically say, okay, we have now, let's say that we have 2 epsilon plus delta half, right? We basically calculate it now, because if we know 2 epsilon plus delta, we can actually calculate this, and we calculate this. So we get the 3 epsilon prime, 3 epsilon. So when we go back here, right, we know something about the epsilon plus delta and all that. So we just substitute, and we get this relation. Okay. So the idea is you construct a meromorphic function on the torus, right, which have some nice invariant properties. Then you calculate the residue, and then you basically, because you calculated the residue, you obtain this kind of relation. Now, what do we see in this relation? This relation is actually very, very, very beautiful. Why is it a beautiful relation? Because you actually have a connection between the derivative evaluated at 3 epsilon prime, at 3 times the characteristic, and here's the derivative evaluated at epsilon prime. Okay. On the other side, what you have the theta cube evaluated as a certain characteristic, and here you have theta prime half half. But theta prime half half, you know that you can replace it by the product. So here, what you see, that you have basically an identity where here, where on the right-hand side, right, you don't have any derivatives involved at all, because you can replace this Jacobi derivative by this product that I showed you in the first slide. Okay. So now the question is, how do I get rid of these primes, right? Because if I want to express, this through a rational combination of theta functions, right? What I need to do, I need somehow to remove these theta primes. I need to somehow get rid of them. Well, it's actually easy. Because what you have here, you have a multiplication by 3, right? If you take, let's say, a number, let's say you take a prime, I don't know, 17, okay? And now you start with 1, you multiply by 3, you multiply by 9. At the end of the day, you will come back to 1 because it's 3 because of Fermat's theorem. So you have periodicity inside these functions. Do you see it? Very simple. You have a periodicity here. Because when you start to multiply let's say you have a characteristic here, which is, let's say, 1 over 17 to 3 over 17. You multiply by 3, you have to go back at the end because of Fermat's theorem. So that's the idea. Now we are going to get rid of one of the derivatives, and we are going to have only one derivative here, and we're done. So here we are actually, so here basically we have this operator, which is we call 3 to the k m mod p divided by p. Okay, and you can see that this operator splits into orbits. Okay, so basically then each orbit has invariance underneath. So here's an example. If you start with the characteristics 1 over 11, this is going to be your orbit. 1 over 11, 3 over 11, 9 over 11, 5 over 11, 4 over 11. If you start with the characteristic 2 over 11, you have 2 over 11, 6 over 11. So 6 times 3 is 18. 18 minus 11 is 7, right? So this is where the 7 coming from. Now 7 times 3 is 21. Minus 11 is 10. This is where 10 is coming from. And then you deliver the Cope de Grace, right? 10 times 3 is 30 minus 8. This is where you are getting it, right? And then when you say, okay, 8 times 3, 24, you go back here. You're done. Okay? So the action of 3 basically splits your residues of 11 into invariant orbits. Okay, so this is basically a more detailed analysis of what's going on. So this is a prime non-divisible by 3. Let's say if you have a prime divisible by 3, then you have a more granular analysis based on Euler's theorem. So this is an example, let's say, of p equals 4. Okay. And we have basically, we include, okay, so now let's go back to, okay, so now let's go back here, right? So what we see that we have invariance under the action of 3, right? Well, if you have this, okay, what you can do, you can start multiplying by 3, and then you are going to obtain a system of linear equations, which involves theta prime, okay? But you have invariance, so it will involve theta prime. Here it will be theta prime as well from the same orbit. On the other side, right, you are not going to see any primes, any derivatives. So here you are going to see derivatives, but here you are not going to see derivatives. Well, this is just a system of linear equations. We're done, because I'm going linear equations where the unknowns are actually the theta primes. So I actually was able to represent, right, a system of basically linear equations where the theta prime, okay, is my unknown. So in this case, for example, if I look on the case of 11, okay, it will be a system of linear equation involving theta prime of 1 over 11, theta prime of 3 over 11, theta prime of 9 over 11, theta prime of 5 over 11, theta prime 4 over 11. When I multiply by 3, I go back to this 1 over 11, and I'm done. So how do I solve it? Well, I solve it using Cramer's rule. That's it. I'm done. So basically, you can see here on this left-hand side, you see the theta prime. On the right-hand side, you see this long formula, which basically doesn't involve anything other than theta prime. All the other characteristics are not derivatives. They're just theta primes. They're just thetas. So what you see here, you're kind of proving a theorem, right? That if you have theta prime as one of your additional functions, you can express any theta prime through this guy and the other theta functions. Okay, The idea is where this formula is coming from. This is just Cramer's rule. The idea is here. The idea is to understand that here you have invariance under the multiplication of 3. So what you will see here, you basically obtain a system of linear equations that connects theta prime with theta epsilon epsilon prime. That's it. You're done. So here's some examples. So when we do this when we do this kind of tedious calculations, and it was programmed by my co-author into Mathematica, you kind of see all these relations which were obtained by people before, even by Ramanujan. We have no idea how they were obtained, but here we just see them as a consequence of this general formula. And by the way, you can see that it's a rational function because here you have to the -1, right? So this sum here, that's what gives you a rational function. From here to here, right, you have a product. Here you have basically a product of theta functions. That's why we claim, right, that this is basically a rational function. And if you look at the degree of the rational function here, divide by this, you will see that it is exactly 3. Okay, so basically these are new relations. Theta prime, theta prime 0/3 equals to some characteristics, but you see here that you divide by theta to the -2. So you kind of see this kind of relations here, and now we have a plethora of relation for 4. Now, why did we include these relations? Because you have products. You don't have these sums. The sums in this formula, in this big formula for small primes, collapse into products. That's what happens here, right? This sum will collapse into products. So that's why we included it, because we thought it would be a nice addition to our presentation. So for p equals 4, p equals 3, p equals 4, p equals 5. You see, for p equals 5, the relations are getting a little bit more complicated, but they are still, we can still handle them. Okay, so this is basically the theta prime 1, 1, and now here, right? You basically have this. Product. You have this quotient. Okay, this is for p equals 6, a non-prime example, and basically we have some vanishing here, some interesting phenomena, and basically now Matsuda, right, is the Japanese guy. He used some how did we know about this? How did we come up with this technique? When I was in my PhD thesis, I did this not for the derivatives, but for the functions themselves. I did this in my PhD thesis. So I knew about the residue theorem, but at the time when I did my PhD, I did not believe that I could use the residue theorem to calculate relation between derivatives, right? But when I saw, so there were a couple of people, there was a Japanese guy by the name of Matsuda that did something, but he didn't do it with residue theorem then. But when I looked on what he did, I understood exactly that this can be done using the residue theorem. So that's how I came up with this technique. So, the bottom line is that if you look on these formulas for theta functions, they're very, very annoying, very formidable. And when, you can't teach them, that's why they were abandoned as part of the course curriculum for the math undergrads. Because in the 19th century, not to teach theta functions would be considered an insult to people. Okay, so basically the idea here is to replace all these formidable options by all these formidable formulas, right, that nobody can find the legs and the hands anyway, with this simple technique of the remainder of the residue theorem, and then some invariant properties of of the characteristics when you multiply them by 3. So, okay, so thank you. So basically, that's what I wanted to tell you, and I'm open to questions.
Thank you.
Thank you very much.
Thank you very much. Any questions, please?
Yes, may I ask you?
Yes.
Yaacov, first of all, let me say that I am very glad to see you once again, and I hope that you will come next year.
I will come. The only reason that I did not come because Borispol was closed. The moment Borispol is opened, I don't care about anything. I'm going to go visit you in Kiev. No worries about that.
I ask you the question, two questions. First of all, you use here this multiplying by 3, but is this technique works for other prime numbers,
yes,
or not?
Yes, the prime. Yes. If you multiply by 5, for example, or by 7,
so you can get similar identities.
Yeah, but with higher order derivatives.
But another question is, if you try to make the derivative of your identity, so something like that. So can you get relations on second derivatives or derivatives of higher?
Yes, we can. Yes,
and you can express them exactly via the values of a function, or you need the values of derivative?
Yeah, but if I have a value of derivative, which I already express a value of a function, I can just plug in, right? So there will be a recursive formulas there.
It was interesting if you have, for instance, where the derivative is 0, then to having a second derivative or higher, you can get the type of critical points. What is it? It is maybe interesting thing, not just where are critical points or where are zeros, but type of them.
Yeah, yeah, I understand what you're saying. Yes, I mean, people, in the 90s, I mean, there were some works by Hurwitz where he didn't use this technique, but he derived the differential equations between first order in tau and the theta function itself. But this, right? So there you could see exactly where, when with this critical point story that you're talking about, because it's more interesting to do it in tau because it kind of lives on a Riemann surface. Here it lives, the z itself lives in in the elliptic curve, but when you substitute 0, you look on tau, you can think about this as basically covering some Riemann surface, and that's where it's more interesting. So yeah, I've seen this done by Hurwitz and other people with the differential equations with Riemann surfaces, but I do not know yet whether this technique can yield the results. I mean, and then it will be actually what you want is this critical point things.
No, because if you know about critical points, maybe you could use something like more theory. So at least you can even if this residue theorem is just a variant of Morse theorem. So if you know the topology of these critical points, you could get just by as a gift you can get more relations.
I understand what you say. I understand exactly what you're saying. I didn't think about this being in this direction, but it might be something to explore.
Yes, thank you very much. Very interesting. Very interesting. Thank you.
You're welcome. And this is a joint work with Julia Bernaska, which I'm sure you all know. Or
yes, please send my greetings to Julia.
Okay, I will. Any other questions?
Yeah.
Good. Okay, I hope you were following, and once again, thanks for inviting me to talk.
Okay,
and hopefully I'm going to eat bычки in Odessa next year.
Okay, thank you.
You're welcome.